Assassins, to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. So welcome back to the weekend, my fellow assassins. We have quite the jam-packed episode for this week, if I do say so myself. Now, I know I've said that before in other episodes, but this one is, I think, significantly jam-packed, partly because Apple just out of nowhere decided to drop some products on us, and I also wanted to talk about some intricacies with multi-threading that you might not necessarily think about when you think of the idea of multi-threading. Because when you think of the idea of multi-threading, you think, this is the fastest way to do something because you're taking advantage of multiple threads and multiple cores, and it's just a great way to do it. But depending on the strategy that you implement, you can actually see a pretty noticeable decrease in performance compared to just not hyper-threading at all. So you definitely have to be careful with what you do and how you do it. So that is coming up on this week's episode. But first, let's get into our trivia question for the week, which, in the spirit of C and C++, this question, which, by the way, all software developers, you better get this one right. And if you don't, you're either most likely a new developer that hasn't really gotten super deep into software development, which is totally okay, or you're a web developer. Either way, here is your question. The question for this week is, when using a memory allocator, such as malloc from C and C++, to request memory from your operating system, where does the memory given to you come from? So when you're using a memory allocator, like malloc, when you call malloc, where does that memory that gets returned to you, where does that memory come from? That is your trivia question for the week. Now, let's get into the cybersecurity tip of the week. So for this week's cybersecurity tip, it's going to tie in pretty closely to last week's cybersecurity tip. And for this week's cybersecurity tip, one thing that is fairly common amongst cyber attackers is to send out phishing emails. And the point of sending out these phishing emails is they'll send you something like, hey, your account's been compromised, or there's been activity on your account that's suspicious, or something to make you want to go log into your account to make sure everything's okay. Now, there's some pretty big issues with this when they send it out, and these are the things that I want you, this is where the security tip comes from. So whenever you get an email from anyone, any organization, anything, you need to verify two things first. The first thing you need to verify is the address of the emailer. And then you also need to verify what link they're trying to send you to. So if, say, Facebook.com, Facebook is sending you an email saying that something about there's like an issue with like your account or something, make sure that the email, first off, make sure the email is actually from a Facebook email. If it's some random string of characters at gmail.com, that is totally not legit. So totally just ignore that email, throw it in the trash where it belongs. And the other thing you want to make sure about is kind of like we talked about last week with making sure that the URL is legit. Make sure that the URL that they're trying to send you to is actually the correct URL for whatever, service or account or whatever that they're trying to send you to. Make sure it's not like a random string, or like we talked about last week, they kind of sort of have the name but like change some letters for numbers and kind of make it look similar but not exact, or they'll have the name of the site dot something else random dot whatever. So that's something that you also want to be sure to check out. And at the end of the day, if you're really unsure, the best way to go about any of these kinds of phishing attacks or something that you're not sure is a phishing attack. So like, for example, if your bank supposedly your bank sends you an email saying that there's been suspicious attack activity on your account, please go log in to verify that it's you, and you're not sure if the email's legit, one thing that you can just do is just ignore the email, ignore all the links in there, go to your bank's site directly and just log in like you normally would. And if there actually is a problem, there should be some kind of notification somewhere, whether that's like right when you log in, a pop-up happens, or there's like a notification icon somewhere on the screen letting you know that something's actually happening on your account. So that's one way you can do it. Another thing you can do, which this might sound crazy to some of you, is you can actually use your cell phone for its intended purpose and call the organization that supposedly sent you the email and see if it's legit. So like if, you're banking with Bank of America and supposedly they send you an email about possible data breach and you need to log in to change your password, you could call up Bank of America and be like, hey, so I got this email that you guys said there's a potential data breach and my password might be compromised. Is that legit or is that a phishing attack? And they'll be able to tell you, basically right away, like, that's legit, that happened, or no, that didn't happen. So that's one thing to make sure. So that is your cybersecurity tip for the week. So now let's get into what nerdy stuff have I been up to this week. So this week, I got to experience one of the biggest negatives of living with a full-blown data center in your house without any of the positives. Now, I would say all of the negatives without any of the positives, but I didn't have anything break on me. Well, I guess something technically did break on me, but it wasn't anything to do with my home lab, and it wasn't this week. But you know what? Let me just show you, or I guess let you listen to what's going on and let you kind of gather what I'm talking about here. So I am currently upstairs right now in my home office where my server rack sits, and I'm not sure if you're able to hear it or not, but I'm standing literally right next to it. I'll give you a second to maybe listen to see if you can hear it. So it's there, but once like the AC or the heat kicks on, it's just absolutely covered by that, and all I hear is the AC. Now, granted, the Xserve isn't turned on, but I have a question for you guys. Why is it that it's so quiet in here, but then as I move throughout my house, going down to the main floor, as you can hear, there is a lot of fan noise? And no, I did not get a second server rack to be on the main floor. And as you can hear now, as I step into the bathroom, there is definitely a lot of fan noise. Now, I wish that this was a new server rack and new data center that I got installed, but alas, it's not. So if any of you can enlighten me as to why my server rack and data center upstairs is so darn quiet, even though I'm running enterprise gear compared to this bathroom, I would greatly appreciate it. So as you could definitely hear there, my home lab got absolutely embarrassed in the noise compartment. It's probably, at the time, it was probably, walking around like a dog with its tail between its legs because of how embarrassed it was. But now the question becomes, I've mentioned before how loud my Xserve is. Is it possible that my Xserve can bring my home lab up to snuff and give it and, be what it takes for my home lab to take back the crown and be the loudest thing in my house? Well, I'll let you be the judge of that. Alright, so now I'm definitely certain that you can hear my home lab right now. I have booted up my Xserve, and it is currently idling right now, as you can definitely hear. But the strange thing, and I can't believe I'm saying this, if we walk outside of my office here, and we enter into the rest of my house, and as we start going down the stairs, the Xserve becomes inaudible because of the other fans currently running in my house. And again, I wish this was another data center, but alas, it is not. So I cannot believe I'm saying this right now, but my Xserve is actually pretty darn quiet compared to the other fans currently running in my house. So I don't know, maybe I'll just have to keep my Xserve on all the time now, because in comparison, it's pretty darn quiet. So yeah, my Xserve was pretty darn quiet to that data center wannabe that was in my house. So basically what happened was, when I was off on vacation, sometime when I was away on Christmas, there was a pipe that kind of blew up in my wall in my bathroom down there. So they brought in those like big industrial fans to like air everything out. It's dry now. It's all good. Well, the house is still a little bit of a mess, but that's not exactly a nerdy thing. The reason I brought this up was because I thought it was funny that, you know, you talk about enterprise servers, they're kind of known to be like these really loud machines, yet they basically sounded like passively cooled mini PC systems or Raspberry Pis or something when compared to those fans, which I thought was kind of funny. Now, things I guess I did actually that were nerdy this week. I did a lot of little things. So one of them was, I was like optimizing some of the scripts that I had and some of my Ansible playbooks to be a lot more versatile and universal. And then another thing I did was I also changed some of my config files around and kind of consolidated things, because before what I had was, in some cases, a different not a Git repo, but a different Git branch for each one of my machines, and trying to like manage all those different repos and not overwrite things that I didn't want to overwrite, and merging everything together and taking the changes that I wanted but not others. It was a massive headache. So now that everything's just kind of all in one branch and everything works seamlessly across all my devices is definitely a big win. And then another thing I did was I actually wrote a new Ansible playbook. Well, actually, I guess I wrote two of them. The first one, which was pretty cool, was an Ansible playbook to install my home lab certificate on all of my servers. Now, I mentioned a few episodes back about creating my own, basically my own root certificate for my home lab, so I can like sign my own certificates and not have to deal with that banner saying that like this website's unsafe and all that. So I wrote a playbook that'll automatically deploy that root certificate to all my servers. So if I want to pull down like something from my locally hosted Git repo or something like that, I don't get an error message saying that like the certificate's invalid. So it was probably just like kind of a one-time use type of a thing, but it's just kind of nice to have in the back pocket, something to reference. I think it was on the Home Lab Show podcast. They talked about like basically just, even if you don't necessarily use them, just having like a library of Ansible playbooks that you can kind of go back and reference whenever you're writing new ones, which I've definitely made use of, looking back through old Ansible playbooks to find things on how to do certain things and incorporate them into new ones. So that's been definitely very helpful. And another thing, which we'll get into a little bit in, not the next nerdy thing, but the one after that, about Red Hat. So I mentioned a few episodes back about I made like a Red Hat template for a Red Hat server. And one of the drawbacks of doing that is the configurations on it is always going to be the same. So like the same IP address, same host name, same SSH keys, all that stuff. So what I did was I wrote a playbook that'll automate the process of setting it up to be a new machine. So basically changing the IP address, resetting the SSH keys, changing the host name, adding a new user, all that good stuff to make it, a new machine. So I don't have conflicts with all of the operating systems running Red Hat. So that was also a fun little project. And another thing that I did was I was really trying to work on my Vim skills now and customize my vimrc file. Now, if you're unfamiliar with what Vim is a text editor. I think it's usually closely compared to VS Code or Visual Studio Code amongst the developer world. Both of them have plugins you can put in. Vim is super highly customizable, but there's a couple big things that it's known for. It's known for it being a command line application. I guess there technically is a GUI, but it basically kind of works the same way as the command line version. So you're running this from the command line. So right off the bat, you have no mouse support, which is a deal breaker for some people. And because there's no mouse support, another thing it's notorious for is having an insanely steep learning curve. Now, I will say that getting into it and customizing my own vimrc file, which is your custom config file, you can in that you can set different settings, remap keys, add shortcuts, all that good stuff. So that's definitely helped, but it is notorious for its super steep learning curve and the infamous meme of one does not simply exit Vim. If you have not seen that meme, highly recommend you go look at some one does not simply exit Vim memes because it's notorious. There's numerous instances out there of people being unable to exit Vim, so they resort to, if they're SSH'd into a client or on a system in the terminal, having to completely close out the terminal, completely exiting it out, or even funnier, if they are physically plugged into the system and there's only a command line interface, they enter Vim, they have no idea how to get out of it, so their only option is to hold down that power button and shut it off and turn it back on again. So that's obviously not the ideal way to close out of Vim, but it's definitely one of the funniest ways to close out of Vim. So yeah, but the reason why I kind of wanted to improve my Vim skills was, as you all know, I have a lot of different virtual machines and servers that run Linux, and one thing that it would be nice would be when I'm, SSH'd in, remoted into these systems, to be able to easily navigate through and editing different config files, or if I want to do some development on these servers, can just develop directly on them through a text editor that I'm comfortable with Vim in this sense. So just trying to, and the other thing too is Vim is essentially it's not standard on every single Linux distribution, but it's pretty much on almost all of them, and it's pretty much on any Unix-based system. It's on Mac OS. It's on most versions of Linux. So, it would just be nice to have that one kind of reliable thing that you can always just go to and be able to be comfortable with and navigate around. So I've been trying to work on that. And I also mentioned the installing a new Red Hat instance. So I found out that there is a Linux version for one of the services that I had to use a Windows server for. So I migrated that service over to Linux, and I used Red Hat for that. And I have to say, if you're not, this shouldn't come as a surprise to anyone, but the performance on the Linux version is a bajillion times better. It's a lot more responsive. It boots up way quicker. It's just faster all around, which makes sense, right? It's Red Hat, so, and it's the server version of Red Hat, but just, any server Linux operating system without the GUI or anything would obviously be a heck of a lot faster than a Windows install that has a GUI in it. But also keep in mind that the Windows version I was using was my custom Windows image, which is already pretty much stripped fairly bare bones as it is. So it just kind of goes to show how much better optimized Linux is to be a server OS than Windows is. So at this point, there's really only 2 Windows servers that I have right now in my home lab. The one is my Windows deployment system, where I am able to deploy my custom Windows images and store them. And the other one is my development environment for Windows, so I can actually build applications and test applications on Windows. And I guess I technically have another one too, but that's just a VM that I use to create new custom Windows images. But unless I'm actively creating a new custom Windows image, it's just powered off. So I don't know if that really technically counts because it's never turned on. So like I mentioned, I decided to use because I have this Red Hat template. I decided I'd make use of it and run this service with a Red Hat VM. And the nice thing was I didn't have to add any additional subscriptions to my Red Hat account, which was awesome. So if you're wondering how I did that, I did an episode a few episodes back talking about the essentially this infinite money glitch that is with Red Hat, where you can basically make a free developer account, and then I think you get I want to say it's 15 free licenses, but basically I kind of accidentally sort of found out that if you install it and you make it a template on Proxmox or something, and I'm sure it would work on VirtualBox or VMware, any other kind of virtual machine solution, or maybe even cloning it on a physical machine. I haven't tried that though. But as far as you creating a template or cloning the virtual machine, it doesn't add any additional accounts to your subscription. So you essentially can clone as many as you want and not have to worry about it. So yeah, that's some of the nerdy stuff I did. Now moving into the bombs that Apple dropped this week. So they dropped a couple of new Macs. They dropped a new Mac Mini, and they also dropped new 14-inch and 16-inch MacBook Pros. Now, there was some speculation that I saw online about if these were supposed to drop maybe back in October, since there was rumors going around that time that there was going to be a Mac event in October where they were going to unveil them, but maybe they didn't have the stock or the inventory, or there was some delays with the supply chain, or whatever the case may be, they didn't end up launching them. But the evidence that these people had to support this speculation was Apple actually released a video unveiling the new Macs, which I didn't watch it, but I saw some clips of it, and it looked oddly similar to any one of their keynote events that they've done, any one of the virtual keynote events that they've done, and it looked ominously similar to one of those. It was also about 20 minutes long, which is also kind of how long those segments kind of are in those videos. And I believe I also heard mention that it started out in the middle of a transition phase, so kind of also leading credence to this was part of a larger keynote that they just kind of stripped out. So that was kind of interesting. But as far as the Macs themselves, the Mac Mini gets the new M2 and M2 Pro chip, and the base model M2 actually gets a $100 price cut, which is pretty nice to see. So the base model now starts at $599 rather than $699, and the M2 Pro starts at $1299. So as far as what you get for these, so the base model M2 comes with an 8-core CPU, 10-core GPU, 8 gigs of RAM, but you can configure that up to 24 gigs of RAM. By default, it comes with a 256 gigabyte solid state drive. You can configure that up to 2 terabytes if you want to. If you want to sell a kidney and give your left arm to Apple, you can definitely upgrade that storage to 2 terabytes. And you can also upgrade to 10 gig Ethernet, which is pretty cool. And you also get 2 Thunderbolt 4 ports with that as well. Now, if you step up to the M2 Pro, the base M2 Pro comes with a 10-core CPU, although you can upgrade that to 12 cores. And it also comes with a 16-core GPU with a max of 19 cores, which I don't know about you guys, but 19 cores for anything like computer related just sounds weird. So that's interesting. But by standard, it comes with 16 gigs of RAM. You can upgrade that to 32 gigabytes. Again, if you want to sell your other kidney for that, you can. It also comes standard with a 512 gig SSD. But again, if you want to sell some of your other organs, you can upgrade that to 8 terabytes. Because we all know how insanely overpriced Apple's storage prices are. And then 10 gig Ethernet, and this one comes with 4 Thunderbolt 4 ports, which is pretty cool. And then moving over to the new MacBook Pros, really not much changed here. The pricing's still the same. Really the only difference is the chip, and now the HDMI port can output 8K at 60 frames a second and 4K at 240 frames a second, because we all know that's exactly what we were missing in the other ones. But jokes aside, it is, good for like future proofing, assuming you're not some YouTuber that's going to be upgrading to the new one next year and longevity of device doesn't matter. But for us normal people that keep our machines for years and years and years, or maybe even over a decade, it's some pretty good future proofing, because 8K, I think really the only 8K things out there are like TVs, and those are like pretty few and far between and like super expensive right now. But who knows what it's going to be like in 10 years. But anyway, as far as the chips on them, they come with either the M2 Pro or the M2 Max. The 14-inch MacBook Pro has the same chip as the Mac Mini with the 10-core CPU or up to 12-core GPU, 16-core 10-core CPU, 12-core max for the CPU, 16 cores for the GPU, and max of 19. But the 16 actually comes base with the 12-core CPU and the 19-core GPU as far as the M2 Pro is concerned. Now, both the 14-inch and the 16-inch, they both get the M2 Max. The M2 Max comes with 12 cores and 30-core GPU by default, but you could upgrade that to 38 if you wish. And both machines start with 16 gigs of RAM and up to 32 gigs if you go with the M2 Pro. And if you go with the M2 Max, you actually start with 32 gigs and a max of 96 gigs, but the caveat there is you can only get the 96 gigs if you opt for the higher end M2 with the 38-core GPU. Otherwise, your max is 64 gigs. And similar to the higher end Mac Mini, 512 gig SSD is the base for the Pro model, up to 8 terabytes. And then if you opt for the M2 Max model, you start at 1 terabyte and can go up to 8. And both the Mac Pros and the Mac Mini MacBook Pros and the Mac Mini are available to order now if you want. And the other thing that Apple released was, do you guys remember the HomePod? Remember how it didn't sell well and then Apple killed it off? So they decided to bring it back for some reason, and if you want it, it's $300. So cool. Now, I guess if any of you are asking if should you buy it, obviously that's up for you to decide. But here are some of my quick recommendations. First, do you want a Mac? If you don't buy one. If you already have a Mac with Apple Silicon, don't buy one. The only caveat to that is if somehow your workflow can't keep up with your M1 something chip or your M2, if you fall into that category, you probably know. But otherwise, yeah, if you have a chip with Apple Silicon, don't buy one of these new ones. Do you already have a Mac that doesn't have Apple Silicon? If you do and it's natively supported, I'd say probably hold off, just because if you still have support, I mean, unless you really need the added performance or battery life, or you have money burning a hole in your pocket, I mean, I don't personally see a reason to upgrade unless you feel like you really, really need to. Now, obviously, if you're coming from a non-Apple Silicon device, like an Intel device, you're obviously going to see a pretty noticeable jump in performance compared to your current system. But again, like, unless you're noticing that your workflow is hindered or like your battery life is garbage now, if your device is currently supported, personally, I don't really see a reason to upgrade. But if your device isn't currently supported, if the new machines are within your budget, I mean, sure, there's definitely nothing wrong with that, especially since you're going to see a pretty darn significant performance increase there. But otherwise, you can easily just, use OpenCore and get the latest OS anyway. So that's not that big of a deal unless your Mac isn't able to keep up with your workflow. Then obviously, if you upgrade, that's not going to be an issue. And then if you don't have a Mac with Apple Silicon and your Mac isn't in any one of those categories, say you don't even have a Mac, then assuming that your budget allows, I mean, sure, go ahead, knock yourself out. As for me, am I planning on upgrading? No. I'm still rocking and rolling with my decade-old Mac Mini from 2012, that quad-core i7, still kicking butt. Granted, it would get its butt handed to it by any of these new machines for sure. But for what I need it to do, it performs everything I need to do adequately. As far as my MacBook Pros I have, one of them is still currently supported, so I mean, I have no plans on upgrading it. My other MacBook Pro isn't supported, but I have it with OpenCore, and it's running the latest OS, and it's doing everything I need to just fine. And then as far as my Mac Pro, it's from 2009, which technically, I guess it's more like a 2012 Mac Pro because I did the firmware mod to it and have the newer Intel chips in there because I did the firmware mod. So, and I've had zero issues with performance on that thing. That thing kicks butt. Now, granted, the new chips, like the Mac Mini, for example, could probably smoke it and do it at like a fraction of the power. But still, I mean, I'm not going to upgrade. So yeah, that was Apple's bombshell that they dropped this week. Now I want to talk about multi-threading. So we did an episode a while back on multi-threading versus multiprocessing, which if you haven't listened to that episode, you're definitely going to want to check that one out because this episode isn't going to go quite as in depth in the nitty-gritty as that one went, as far as like comparing multiprocessing and multi-threading and kind of how they work. But this is just kind of going to be more of a deep dive into like kind of methodologies of multi-threading itself. Now, if you're a software developer like me, when you were learning software development, if you're like me, multi-threading and parallelism was essentially an afterthought. Especially if you went through any kind of education system where they teach you how to code, generally they don't really bring up any kind of multi-threading or parallelism. And if they do, it's just kind of like, oh yeah, I guess, last week of the semester we got like one more class. Here's how multi-threading works. Here's a dummy example. And that's kind of the extent of it. And the impression that I got was whenever they demoed it, it was always slower, and they always mentioned how complex it was and how much overhead there was, and basically kind of made it sound like it wasn't worth it. And which, I mean, the demos they showed, it obviously wasn't worth it because not doing any multi-threading was faster anyway. So yeah, more complexity, slower, and hard to wrap your brain around. What's the point in doing it? So that was kind of my takeaway when I went through the education world as far as multi-threading is concerned, which is weird because when you think multi-threading multi-threaded applications, what you think about is you think that's the way that you take every ounce, you can pull every ounce of performance out of your system. Yet, whenever I was exposed to it, it was always like how you slow down your system. It did the opposite of what it was supposed to do. And there's really two reasons of why this is the case. The first one is scale. And obviously, if the code that you're working with is small, multi-threading isn't going to help you. It's only going to be a detriment because, as we mentioned in the episode where we talk about multi-threading and multiprocessing, there is overhead involved when dealing with multi-threading. It's not like you can just flip a switch and you instantly can go faster. There's a lot of stuff that goes on under the hood that has to be done before you can take advantage of that, the speed increase of doing things in parallel, which if the scale that you're working with isn't big, the overhead is just going to negate any kind of performance that you're gonna see. So it's like if you imagine doing a quarter mile race. If it doesn't matter if your car can do 0 to 60 in 2 seconds and has a top speed of 250 miles an hour, if you're going up against a Toyota Prius or something, if your car takes 10 seconds before you can start it and get off the line, you're gonna lose anyway. It doesn't matter that you're faster. So that's kind of the thing as far as scale is concerned. You have to make sure that the scale is big enough where multi-threading can actually overcome the overhead and actually improve your performance. And the second reason why multi-threading might be slower is the implementation used was hot garbage, which is kind of the theme here, which I kind of want to get into, whereas not all multi-threading is created equal. Just because you have a multi-threaded application doesn't mean it's optimized and doesn't mean you're using it correctly, I guess you could say. So to show this, I actually ended up writing 3 versions of the same C program. So the first one was just a baseline C program, and then the other 2 had 2 different versions, 2 different implementations of multi-threading. And each, for standardization's sake, each implementation had 4 threads assigned to them, so it wasn't like one had 10 threads and one had 2. They both had the same number of threads. The only difference between them was their implementation. So the point of this program was to take an array, and that same array would be used in each one of these different versions of the program. So I made sure I had the exact same array so it'd be standardized. So the same array was passed into the baseline one with no threads, and then each one of the implementations. So one thing that I guess I want to clarify real quick is in C and C++ and other programming languages out there, they don't have a concept of multiprocessing. They're multi-threading and multiprocessing, as far as C and C++ is concerned, is one and the same, which is in contrast to Python. Python has multi-threading and has multiprocessing. So the big difference is in Python, if you create a multi-threaded application, it's only going to run on one CPU core. It doesn't matter if you spin up 10 threads and you have a 16-core machine, you're only going to be using one CPU core even if you have 16 threads, which is in contrast to if you do it in C or C++. If you spin up 16 threads and you have a 16-core machine, chances are you might be using all 16 cores for all of your 16 threads. So as far as Python is concerned, if you're working in Python and you want to ensure that your code is running in parallel and running simultaneously, you need to ensure you're using multiprocessing. And if you want to hear the difference between multiprocessing and multithreading, again, there's another episode that we did on that, so you can go listen to that. But just because the multi-threading in Python is only able to run on one CPU core, that doesn't mean it's entirely worthless. Because as we mentioned in that episode where we talked about the differences between multi-threading and multiprocessing, if you have a really I/O heavy task, like a lot of reads and writes to files, or you're waiting on user input or something like that, multi-threading will still speed things up for you in Python, even though it's only running on one core. And the reason for this is because how the operating system and the CPU works is at the low level, there's a scheduler that basically assigns tasks to the CPU cores and all that stuff. So basically, if you have multiple threads running and one thread is waiting on input from, say, the user, but you have another thread that's doing calculations in the background, what your one CPU core can do is when it realizes it's hit that roadblock waiting on user input, it can transition to the other thread and go start doing that computation in the background. And then when you as the user enter in that user input, it can then switch back, handle your user input, and then go back to the other thread dealing with the computation. So you can still potentially have speed improvements with multi-threading in Python, but that's definitely the biggest difference between like Python and C and C++, where multi-threading in C++ and C is essentially the same thing as multiprocessing and multi-thread. They're one and the same. They're used interchangeably because they mean the same thing. So an example that's outside the computer world is Python's implementation of multi-threading is essentially what it's like cooking by yourself. So if you imagine when you're cooking by yourself, you can either cook everything you want to cook and then you can clean up, and that'll take a set amount of time. Or you can cook, and then while your food's cooking, you can incrementally clean things up while your food's cooking and you're just kind of waiting around doing nothing. And that way, when you're done cooking, you don't have as much to clean up and you're done quicker. So that's essentially what multi-threading in Python is like. There's one core, just like when you're cooking by yourself, it's just you, but you can do multiple tasks at the same time to speed up the overall time that a given thing will take. So that could be might help some of you out there kind of understand multi-threading when it comes to Python. Now back to the C programs. So as I mentioned, I gave each variant the same array and tasked it with computing the sum of all the elements in the array. So obviously when we talked about this idea of scale, when the array was really small, both of the multi-threading solutions got their butts handed to them. They got absolutely smoked by the non-multi-threaded version because, again, there's overhead involved with spinning up these threads and joining them back together. Now, when we move over to larger arrays with a lot more elements to compute the sum of, one of the implementations performed 2.5 times faster than the baseline with no threads, but the other implementation of multi-threading was significantly slower than both of them. So on the one hand, you have a multi-threaded application that is significantly faster, and on the other hand, you have a multi-threaded application that's significantly slower. So you can see here that just because you're multi-threading your program doesn't mean you're making your program faster. You could be making it slower. And this is where how you implement your multi-threading really comes into play here. Now I should bring up the strategies that I used for this application. So this computing the sum is, you could think of it as a very compute-heavy task. So if you're writing this in Python, this would be a perfect implementation of multiprocessing. But because multiprocessing and multithreading are the same thing in C, there is no multiprocessing. You have to implement your multi-threaded strategy in a certain way. So the two strategies that I implemented for my multi-threading approaches was the first strategy took the array and put a mutex on it, and that way only one thread would be able to access the array at a given time to do its calculation. Now, the reason why you have to put a mutex on it is because if you don't, you get you run into race conditions, which we talked about in the previous episode where we talked about multithreading versus multiprocessing. But a quick recap, a race condition is where you have two threads trying to access the same data at the same time and they overwrite each other. So the most classic example of this is, say you go to deposit $20 into your bank account, but when you're going to deposit that money, say your electric company is taking their auto withdrawal from your account for like auto pay, so you both take hold of that account balance variable at the same time. So depending on who, and say you have $500 in your account, and both of you take that $500 number at the same time. So at the end of the day, you should have $370 left over if you were going to deposit $20 and the electric company was going to take out $150. So you should have $370, but depending on who writes first, you could either end up with $520 if your write happens after the electric companies, or you could have $350 if the electric company went second. So you can see that this is definitely a big problem. So the point of the mutex is to essentially lock down that variable. So if you get to it first, you put the mutex lock on it, so the electric company has to wait for you to update that variable with your $20 deposit before they can get in and access it, so you're not overwriting each other. So that's kind of race conditions, and that's the point of mutexes, so you can make sure that no other instructions can read or can access that variable when the mutex is held by a thread. So in compute-heavy tasks, this is a major detriment because this mutex solution was the one that performed significantly slower than the other multi-threaded application version and just the no multi-threading at all. And as you can kind of think, you might be able to see why, because we have to, so when the thread tries to access the data, it first has to put the mutex lock on the data, do its calculation, and release the mutex lock. Then the next thread comes in, takes a hold of that lock, computes the calculation, releases it, and the next thread comes in. But as you can see, because it's one thread at a time, you're essentially doing it sequentially, but adding extra steps by taking and releasing the mutex lock, and you also have the additional overhead of dealing with threads, so it's just very, very slow. Because you essentially have three threads literally just sitting there doing nothing, waiting to get the mutex lock so they can perform their task. So if you go with this implementation strategy for multi-threading in this case, it's going to be way worse than if you just didn't multi-thread at all. Now, the other implementation was more of a multi-processing, I guess you could say, take on it. So in this implementation, there was even more overhead than just the threads, because what I did was I took the entire array and then subdivided it up to the number of threads I had. So I basically broke the array into 4 chunks, equally sized chunks, and then assigned those chunks to each thread. And then each thread could just compute the sum of their section uninterrupted. Don't even have to worry about mutexes or anything like that, because they're going to be the only ones working on this data. And then once they're all done with their portions of the array, then everything can come back together and be summed up and compute the sum that way. So that's where the significant performance increase happened. So here, this right here is the perfect example of how your implementation strategy for multi-threading can drastically change what kind of performance you're going to see when you're writing your code. So if you're going with a compute-heavy task like this, definitely don't want to be using mutexes on something that needs to be computed like this, because you're just going to slow everything way down. So again, if we kind of take this outside of the computer science world, let's say that the goal is to do 12 pull-ups. And let's just assume, for the sake of argument, that you're, a buff person and you can do 12 pull-ups no problem. So let's just make that assumption. So that would be your baseline solution with no multi-threading. Now let's say you want to do a multi-threaded solution. So let's assume, since I mentioned my solution had 4 threads, so let's just say that your multi-threaded solution has you have 3 of your buddies join you to help you in your quest to do 12 pull-ups. Now, if your solution to do the pull-ups was consisting of you doing a pull-up, getting off the bar, your next friend doing a pull-up, getting off the bar, and so on, that's obviously going to be significantly longer than you just doing 12 pull-ups in a row by yourself. And this is how the mutex works in this situation, because the 12 pull-ups is essentially computing the sum of an array. And you getting on and off the bar to do your 1 pull-up is like you grabbing the mutex, doing your summation, which is doing the pull-up, and then releasing the mutex or releasing from the bar, and then the next thread coming in, doing the pull-up, and so on. So as you can see, that's definitely a lot slower. Plus, you have the overhead of, all of your buddies saying, okay, so this is how we're going to do it, kind of a thing. Now, one solution that would make it faster was, as we mentioned, the faster solution in this case was you divide up the array evenly amongst all the threads and they can run uninterrupted. So even though you have more overhead of telling your friends, okay, so we're all going to jump up on this bar at the same time and we're each going to do 3 pull-ups. Got it? Cool. Then you jump up, you do your 3 pull-ups, and you're done. That's obviously going to be a lot quicker than you doing 12 by yourself. So as you can see, the strategy is almost as important, if not more so, than the act of you saying that we're going to do it in general. So that's not to say, I've been bashing on mutexes here for the past, I don't know how many minutes, but that's not to say that mutexes you should just avoid them and never use them. Because obviously, as we mentioned previously, they're crucial for avoiding race conditions. But another place where mutexes make a lot of sense is when you have blocking operations. So things like I/O, input output, or like user input, or anything that you're going to be waiting on something and you can't just go ham and compute something. So in this case, if you're going to be waiting on something, in this case it doesn't make as much sense to divide up the tasks divide up the tasks amongst the threads, because you could run into a situation where one thread might be on its second task and it's waiting for user input, and you went off, I don't know, go grab a cup of coffee, or you went to go to a meeting or something, and that thread is just sitting there waiting for your input. All the other threads have finished whatever they were doing, but your program can't complete because this thread is still sitting here and has a queue of, say, 10 other tasks that it has to do afterwards. But since you subdivided the work up amongst all the threads individually, those other threads that are just sitting idly can't take on that work and finish the program faster. So situations like that where you have to deal with potential delays and pauses in execution is where using the mutex definitely definitely benefits you, and having just a queue of tasks or something to work on, that once a thread finishes, it can just go grab the next task, put a mutex on the queue, for example, grab the task, release the queue, do its work, and so on. So another good example, real-life example of this, to abstract it from the computer science realm, is, say you're doing house chores, for example, which everyone loves house chores, am I right? So let's assume here that all the chores that you have to do as far as cleaning your house, you put those in a queue, and you and your roommates are essentially the threads in this case, and the queue is that the queue, because a queue is a data structure, but that is in a central location, maybe say it's in the kitchen on the fridge or something, and that's like when you would have your queue somewhere in main or global memory that you would then go access. So basically, just like how you would if you were doing chores in this sense, once you finish a task, you'd go to the queue, go to the list of chores, and make sure no one else has access to it. You'd cross off the next thing that you're going to do, so no one else can grab that at the same time. Because as fun as cleaning toilets are, you don't want two people trying to clean the toilet at the same time, because it's just not going to work. Now, let's say you wanted to evenly divide the tasks amongst everyone. Collectively, you would probably finish slower rather than if you just had a queue. If you had a queue and once you finish whatever chore you were doing, you'd go take the next one. Collectively, that's going to be a lot quicker than if you just divided everything up evenly. Because if, say, Bob over here gets stuck with sweeping and vacuuming the floors and cleaning all the bathrooms, and Josh over here is just washing the dishes and folding the towels, Josh is going to be done significantly quicker than Bob is, but the chores aren't going to be done until Bob finishes. Whereas if this was a queue of tasks, Bob might be sweeping and vacuuming the floors, but Josh already finished cleaning the dishes and folding the towels, so he can go start on cleaning the bathrooms while Bob's still sweeping the floors. And that way, you'd collectively finish quicker than if Bob was, stuck with doing what was assigned to him, and Josh was just chilling on the couch, watching Netflix or playing video games or whatever the case may be. So one way you can even demo this in the code is if you take that same example that I showed you with summing up the array, which I actually did this because I was curious. Actually, kind of a side tangent. When I was coming up with ideas for what to talk about for this week's episode, I was kind of thinking about this section of it, and this idea of you take the code from summing it up and then changing it to using a sleep rather than summing, like what would that look like? And then I was like, you know what? I need to try that. So I implemented it. But if you wanted to, you could also take that same code of summing up the array, but rather than summing it, rather than adding those elements, you basically take whatever that element is and then sleep. Now, personally, I wouldn't recommend sleeping for the value assigned, because by default, it's at least in C and C++, the sleep is in seconds. So if you're summing up, say, an array, and you don't change that, that's going to be a lot of seconds. So personally, what I would do and what I did was divide those numbers by some value, whether it's 10, 100, or whatever, just to make it smaller, so you're not going to be sitting there for minutes on end waiting for your program to work and finish. But in this case, what you'll find is if you divide the array up evenly, it's not going to be the faster solution. Now, will it be faster than no threading at all? Yeah, obviously. It's gonna smoke the no threading solution, because it's able to sleep essentially four sleeps at the same time. But the reason why it's not necessarily going to be faster is because, like I mentioned, if one thread gets the short end of the stick and has all the long sleeps, while it's still going to be faster than the no threading solution, it's not going to be as fast as the solution where each thread just, once it's done sleeping, it takes the next one off the list and just keeps going and going and going. So now, there are instances where dividing everything up evenly will be quicker, but generally speaking, on average, it's faster if you just use the mutex on the array collectively, since once a thread's done, it can immediately go and grab that new one, and then you're not relying on a slow thread that got stuck with the short end of the stick having all the long sleeps, or or I guess you could say in other cases, having a thread that's stuck with a bunch of high, input, output, file read writes, user input, that kind of tasks, that it's kind of lagging behind and its queues building up, or its assignments, it's not taking them down like the other ones are, and then you're just left waiting on that one thread. So in those kinds of cases like this, that's where you want to use the mutexes. So the moral of the story here, I would say the TLDR, but because this is a podcast, I guess it'd be more like a TLDL, too long didn't listen, would be that multi-threading methodology and implementation and how you use your multiple threads is just as important, if not more so, than the act of multi-threading in the first place. Because as we've shown here, you can very easily make your program significantly slower by multi-threading it, whereas if you didn't multi-thread it at all, you would, by comparison anyway to your bad strategy, would be a lot faster. So that's one thing to keep in mind. I definitely recommend that you test out multi-threading, and because it's definitely an important skill to have if you're going to be working on big software projects like that. So it's definitely a good tool to be able to know how to use and have in your back pocket. But the thing that you need to make sure is you need to know what the goal of the task at hand is and how to best implement your threading strategy, because if you don't, you're going to take a significant hit to performance. And the point of multi-threading is to speed up your program, not slow it down. So yeah, there's that. So now we've been talking about C a lot of threading. And if you recall, our trivia question from the beginning of this episode also referenced C, although it wasn't, explicitly a C question, although I related it back to C because I think that's one of the more widely known memory allocators. So to refresh your memory, in case you forgot, this week's trivia question is, when a memory allocator, such as malloc from C and C++, when you use that malloc call, in this case, to request memory from the operating system, where does that memory come from? So that memory that the OS gives you back when you call malloc, where does it come from? Now, if you said the stack, you are wrong. It comes from the heap. So if you said the heap, congratulations, you got this week's trivia question right. I hope all you software developers got it right. Otherwise, might need to go back to and brush up on some of your more lower level language skills. And if you're a web developer, let's just say I'm not surprised you got that one wrong. Because I guess the joke is web developers, they just, they deal with their JavaScript and their HTML and their CSS and their React and their databases, and they don't really deal with, the hardware on a computer. So, but me and some of my friends, we like to give web developers a hard time. And some software it's kind of this funny thing where like the web developers are kind of like their own group and they think really highly of themselves, and then you have everyone else that's not a web developer that like hates them, which is kind of funny. But at the end of the day, we're all developers. We all make the computers work and the internet work and the websites work. So at the end of the day, programming in general is definitely a good skill to know, and it's any kind of software development is good. So I like to joke and hate on the web developers, but I myself have done web development in the past. I maintain a couple websites myself, so I can't hate on you too much. But for me personally, web development is not one, it's not my forte, and two, I prefer other kinds of development rather than web development. But as much as I like to hate on you web developers, know that it's all in good fun, and I don't actually hate you. If you enjoyed this episode, I ask that you leave it a rating and review, and subscribe to the Dark Assassins podcast if you haven't done so already. Also, be sure to share with a friend or family member, especially any software devs out there that that would definitely have some benefit by listening to this big segment we did on multithreading and the methodologies of multithreading and how you could be doing it wrong and making your program slower, and how to make it faster by actually doing it the right way. And I know this was a really kind of dense, deep topic into multithreading. So if you have any questions about it, or you have any topics or questions for future episodes that I could do, shoot me an email at contact@darkassassinsinc.com. There is a link for that down in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.